Okay, good morning. Last class of the semester, right? Whether we are ready or not, it's going to get over. I'll try to wrap up a few things today and also address some questions that I think yesterday it seems like a bunch of people asked questions. So today we are on lecture 29. And so a couple of sort of housekeeping things. I forgot to include 3 pages from the last lecture. So I used these 3 pages in the lecture, but when I gave the sheets to Engineering Online, I forgot to include them. So I've numbered these as 28-27A, 27B, and 27C. So these should come after, obviously 28-27. So I'm going to include them in today's notes. So just put them in the proper place. Okay. The other thing I'm going to do is finish up 2 topics. Finish. TAT, and then it seems like a bunch of people have questions on this. The Newt 1 S0. So I'll talk about that and I'll give an example, and I'll also post this example on Moodle. Hopefully that'll help, and then address any other questions. Okay. So before I proceed with this, any general comments? I think we'll have a few minutes for questions at the very end, but anything else that we should talk about today that maybe is more higher priority or something? Okay, so having said that, let's press on. And I'm going to use pre-prepared lecture notes from previous year. It seems like every year I push these 2 topics in thin airfoil theory to later on, and that's kind of, it seems to have worked out that way every year. So we're going back to thin airfoil theory, and just to complete a couple of topics. One is this ideal angle of attack, and the second is how do you simulate trailing edge flap effects in thin airfoil theory? How do you model that? So ideal angle of attack. This is not discussed very much in textbooks these days. I think it was something that was in many old textbooks, but for some reason it's just sort of fallen out. So what is this ideal angle of attack? Okay, so to talk about that, let's look at the delta P distributions along the chord. So delta P is the pressure difference. So if we have a camber line like this, and that's what we are trying to simulate with thin airfoil theory, and if we take some x location, so there's going to be a lower pressure on the lower surface and pressure on the upper surface, and usually for a lifting airfoil, the pressure on the lower surface will be larger on an average, and so you get positive lift. Right, so this pressure difference is delta P is PL minus PU at some x location. And if you go back and look at how the vortex sheet strength or vorticity distribution along the chord, how that is used to calculate lift. This delta P turns out to be just rho V infinity small gamma of x, right? Recall that small gamma of x is vortex sheet strength at x location. And so this comes from Kota-Joukowski theorem, which says that lift equals rho V infinity gamma dx, okay? Now if you recall thin airfoil theory, the vortex sheet strength is written as a sum of two contributions for cambered airfoils. For symmetric airfoils it's just one, this one is not there. But for cambered airfoils, the way we formulated it is there is a gamma 1 term and there is a gamma 2 term. And to remember and elaborate on this, this is kind of how the two gamma distributions look like. So gamma 1 is the angle of attack term. So this gamma 1 depends on angle of attack. So if you increase angle of attack, you go this way. And decrease angle of attack, it goes this way. So what happens is, as you go to more and more positive values, this term, this gamma 1, which is essentially this expression, will have a singularity at the leading edge, and it will in general increase like this, and all of these will go to infinity. And if you go to negative angles of attack, it will go like this. So this gamma 1, it depends on angle of attack. The gamma 2 depends only on camber. Okay, so this is that Fourier series, 2v infinities summation n to n equals 1 to infinity a n sine n theta. So remember, we added a lot of sine waves, and we selected the sine waves and their scaling factors so that the camber line boundary condition is satisfied. So that depends only on the camber line, it's independent of alpha. So what you do is, depending on the camber line, this gets calculated, and then depending on the angle of attack, this gets calculated. And for a given camber line and angle of attack, you add those two, and that's the solution. So what does this mean? Especially, what does the singularity mean? Obviously, we can't have vortex sheet strength going to infinity in real airfoils. So what happens? So what happens is that in the thin airfoil theory, that's an approximation, right? But especially at the leading edge, the approximation sort of falls apart, because a real airfoil is something like this, a thick airfoil with a rounded leading edge. So in the thin airfoil, when alpha is greater than alpha ideal, okay, so we haven't talked about what is alpha ideal. So alpha ideal is the angle of attack when this contribution goes to 0, and then you'll have only the camber contribution. So let me maybe insert a page there to explain that. So the concept of alpha ideal. I thought I had that page somewhere. Okay, yeah, I think I have it. So it's just in a different order. So here we talk about the concept of ideal angle of attack. So ideal angle of attack, which is denoted by alpha ideal in short, is that alpha at which there is no suction peak on the leading edge on either upper or lower surface, and the stagnation point is exactly at the leading edge of the airfoil. So that means when alpha equals alpha ideal, the vortex sheet strength at the leading edge is 0. So there is no singularity. And this happens when A0 is equal to 0. So going back to the previous page, so we had the sum of two contributions, right? This contribution and this contribution. This you can't do anything about. If you have a camber line, this is determined. But note that this always goes to 0, right? This contribution always goes to 0. So there is no singularity due to this. So the only singularity is due to this. And if you want to remove that singularity, you just choose the angle of attack so that the entire gamma 1 is 0. And this is gamma 1. Here we are writing it in terms of theta, which is just a transformed coordinate for x. So if gamma 1 is 0, the only way to make that 0 is to set A0 as 0. Okay, so this happens when A0 is 0. That means, and A0 is written as, look back at thin airfoil theory, this is A0, and we'll just call that angle of attack as alpha ideal. So if you set that equal to 0, alpha ideal is this integral, which, given a camber line, this term, and so we can get this. But so let's see what this means physically. Okay, before I get all mixed up, let me take care of some page numbering. So this is 29-2. Yeah, and then this 29-3. Okay. So when alpha is greater than alpha ideal at some moderate angle of attack, then stagnation point will not coincide with the leading edge. So stagnation point will come below the leading edge on the lower surface. And so there are some streamlines that will have to go near the stagnation point. It will go on the lower surface, and then it will go around this leading edge, right? And that's what, when you make the flow go around a sharp corner in potential flow, that gives rise to an infinity in the velocity, or in the vortex sheet strength, or in the pressure difference, or any of those things. So that's why thin airfoil theory solution gives this infinity here. But in reality, what happens is that is not a thin leading edge, right? It's a rounded, thick leading edge. So this infinity will actually get softened. So there will be a sort of tendency for the CP distribution to go to a peak, but it won't go to infinity, it will just get rounded off. And that how much it gets rounded off depends on how round this leading edge is. This is when alpha is greater than alpha ideal. When alpha equals alpha ideal, that's when, even in thin airfoil theory, the streamline comes and hits the airfoil, the stagnation streamline comes and hits the leading edge. So it does not go around a sharp leading edge, it just theoretically matches with the leading edge point. And A0 becomes 0, so A0 is equal to 0, that means no leading edge singularity. Right, and so the only distribution is gamma 2. in that condition on the thick airfoil, so if you take the actual airfoil that this is approximating, right, the actual airfoil is thick, the streamline, stagnation streamline will come and hit the leading edge, and there will be no pressure peak on either the upper surface or the lower surface. No suction peak. We usually call that a suction peak, right? And so if you're designing a laminar flow airfoil, remember, so at moderate Reynolds numbers like 1 million to 9 million or something, if you have a suction peak that causes adverse pressure gradient behind it, and so you lose laminar flow. And so this is a condition at which, provided the airfoil is designed with favorable gradient, you will have lots of laminar flow. The leading edge is sort of meeting the flow in a nice way, right? So this is like a sweet spot in angle of attack. So if you have a laminar flow airfoil, this will most likely be at the center of the drag bucket, because neither the lower surface nor the upper surface has a suction peak. So this is at alpha ideal. If alpha is less than alpha ideal, then the opposite happens. So the angle of attack is too low, so the stagnation streamline comes and meets the thin airfoil on the upper surface, and the streamline adjacent to that goes from upper to lower around the sharp leading edge. And so you will have a negative singularity at the leading edge, right? So the vortex sheet strength or delta P distribution will have a negative singularity. If you then take the real situation on the thick airfoil, you will have something like this. So stagnation streamline comes and meets here on the upper surface, a little bit on the upper surface, and this streamline goes around the thick airfoil, and because it's a rounded airfoil, you won't have singularity, you won't have this infinity behavior, but you'll still have a peak, and in our CP distribution plot, that will manifest as the lower surface getting a suction peak. Right, does this make sense? So lower surface getting suction peak means there is adverse pressure gradient here. So this region is adverse. So if you're trying to get laminar flow, this is the point, this is the angle of attack at which the lower surface will lose laminar flow. And if this is significantly less than alpha ideal, then you will have such a big suction peak that the lower surface will separate. Flow will separate on the lower surface. And exactly the opposite condition is when alpha is much greater than alpha ideal. We saw this 2 pages back. Here the upper surface has a suction peak, and so upper surface will lose laminar flow. But in a thick airfoil, it won't happen. So in a thin airfoil, there's just one exact sweet spot, right? Because it's sharp leading edge. So the minute alpha is even a little bit away from alpha ideal, you will get suction peak. But in a rounded airfoil, that's softened, so you can go for a few degrees on both sides and you will still have laminar flow, and that's why you have a drag bucket of a finite CL width. Okay. So how does all this connect to connect to the drag bucket and all that stuff? So when alpha equals alpha ideal, the lift coefficient can be called as CL ideal, right? Ideal lift coefficient. And from thin airfoil theory, we know that this is the equation for CL. Lift coefficient is 2 pi A0 plus pi times A1. That means when at ideal condition A0 is 0, so this term will go away, so CL ideal is pi times A1. And for most airfoils, that CL ideal will correspond to approximately the middle of the drag bucket. Somewhere in the middle. It may not be exactly the middle, depends on the geometry, but it will be somewhere close to the middle. And for CL greater than CL ideal, the upper surface at some point will lose laminar flow. and most airfoils there will be a region when that can be tolerated. So beyond that, this is where the upper surface loses laminar flow. CL less than CL ideal, again after a small CL region of when things are tolerated, then the lower surface loses laminar flow. And so that's why you get a drag bucket, right? A drag bucket is when both upper and lower surfaces have some decent amount of laminar flow, maybe 50% or something. Okay, any questions here? I hope you're able to connect this with what you're seeing in project 2, unless like you're so stressed out with project 2 that nothing is entering, then I mean, yeah, that sometimes happens when towards the end of the semester. Okay, let's talk about the next topic in thin airfoil theory, the last topic in thin airfoil theory that I have in mind. And this is how to model a trailing edge flap. So within the thin airfoil theory assumptions of small angle of attack and small camber, we know that thin airfoil theory is linear. That means you can add different effects and get the combined effect by adding the solutions for different effects. So we can add the geometry changes by determining each geometry change, effect of each geometry change independently. So we're going to use this fact to help us out when we study trailing edge flaps. So we'll study the trailing edge flap effects for a symmetric airfoil, but because you can add stuff up, the deltas that you get for flap for a symmetric airfoil, you can add that to any cambered airfoil and the same delta will apply. So because of that, we'll take a symmetric airfoil. It makes life a lot easier, and we'll just study the effect of a flap for a symmetric airfoil. So symmetric thin airfoil is just a straight line, right? A flat plate. So we'll put the hinge point here. This is the flap hinge. So let's say this is at K times C. So the whole chord is C. K times C is some fraction. So K is like maybe 0.8. That means this is the flap hinge is at 80% chord. And we'll assume the flap is deflected by an angle delta F. So delta subscript F is the flap angle. So with this situation, we'll go and use thin airfoil theory to study this. But we have to remember that thin airfoil theory is really valid only for small camber and any kind of small geometry deviation. So it's really only valid for small flap angles. And the other reason when this particular part of thin airfoil theory easily breaks down is because in an airfoil, if you have a flap, usually you'll have flow separation, right? So even after about 5 degrees or 10 degrees, you might have flow separation. And so these viscous effects will sort of make the predictions from thin airfoil theory not be very valid. So this is one place where viscous effects very quickly start showing up. So viscous effects. Okay, so this is just a sort of side discussion. Okay, so we have to put this in thin airfoil theory, and so we're going to say if this is the flap deflection, this is the location of the flap, as a fraction of chord. And so thin airfoil theory requires this dz dx, which is the slope of the camber line. And because we are choosing a symmetric airfoil, dz dx is 0 everywhere up to this point. So from 0 to kc, dz dx is 0. And from kc to c, for x equals kc to c, dz dx is minus delta f, because that's the slope of this camber line. So we'll put this into all those equations we derived for a cambered airfoil, because this is like a camber, right? Even though it's a symmetric airfoil, this part is essentially like a camber. So we can use all that stuff we did before. As usual, we'll switch to theta coordinates, because then we can do the integration easily. So x equals half c times 1 minus cosine theta, which means we'll also have to convert the x location of the hinge to a theta location. So this x location from here to here, this is x equals kc. That will be converted to a theta location, which is theta k. We'll call that theta k. So theta k is the angular location of the hinge. And so to get that, we say x, which is kc, equals c over 2 times 1 minus cosine theta k. And so cosine theta k is 1 minus 2 times k. So as an example, if you have a 20% chord flap, and so this is terminology that might confuse people, especially if you have not done aerospace engineering in undergrad. So when we say 20% chord flap, that means the flap is 20% of the whole chord. And usually you think of the hinge line as the extent. So this is 20% of chord, and this is the whole chord. That means the hinge at 80% chord, or 0.8 c. So the k is 0.8. So for this condition, cosine of theta k becomes minus 0.6, and you can get theta k. Right? So this is straightforward. So we plug all this back into the thin airfoil theory equations. Once we do that, we can obtain A0, A1, A2, A3, and all that stuff, because we have dz dx. Okay, so if this is not, I think if you go back and look at the thin airfoil theory equations, this will make sense. It's been a while since we did that. So dz dx is 0 for the first part of the airfoil, from 0 to theta k. So we don't even need to consider that part. So we only need to do the integrations for theta equals theta k to pi. And so we go and plug that back into the equations. So A0 is alpha plus 1 over pi integral over the chord delta f times theta, right? So this integration needs to be done only for the last part of the airfoil, from theta k to pi, and so this is what we get as A0. And AN is this equation. Again, we are doing the integration only in the last part of the airfoil, and so you get AN as 2 delta f over pi sine theta k, sine n theta k over n. That's it. Once we have A0, A1, A2, A3, we can take as many n values that we want to improve the accuracy of the solution, and we can get the effect of flap deflection. So it turns out that you can get the most important effects by just considering the first 3 terms, and I think that is A0, A1, and A2. After that, it's diminishing effects. So if you want to do sort of hand calculation, you can ignore all of the higher order terms. So when you do that, I'm going to skip some details and give the sort of answer. You get CL is 2 pi alpha plus delta f times this. Okay, so you have theta k sine theta k here. So depending on the flap angle and the hinge location, you can get a CL. And CMC over 4 is this, which I've reformulated to this value. So again, depending on the flap angle and the hinge location, you get CMC over 4. So if you want to find out what is the effect of a flap deflection on a cambered airfoil, you can just take the delta from this and add it to the camber condition. So you can say from this delta CL, for a symmetric airfoil, CL is 2 pi alpha, right? So this is the delta CL term. So delta CL is 2 pi times delta F times that stuff in the parenthesis. So this is valid for any airfoil. So you can add this to a thin airfoil or to a cambered airfoil. You take a cambered airfoil and if you deflect the flap 5 degrees, you can find out the increment in CL with this. It's going to start becoming invalid once boundary layer separates from the hinge, but until that point it's good. And what is the CMC over 4 for a symmetric airfoil? 0, right? So this itself becomes the delta CMC over 4 due to flap. So you can take this and add to the cambered airfoil any value for a cambered airfoil, and that will be the change due to flap. Okay, and then finally we'll combine these two topics that we did. So that's the effect of flap deflection. So we talked about ideal angle of attack, ideal lift coefficient, and flap. So let's see what happens to CL ideal due to a trailing edge flap. So we know, I forgot the no here, we know that CL ideal corresponds to A0 equals 0, right? So for a symmetric airfoil with flap, if you look back 2 pages behind, A0 is alpha plus delta F over pi times this. If we set that equal to 0, that angle is alpha ideal. So when you have an airfoil with a flap deflection, a symmetric airfoil, alpha ideal is minus 2 delta F over pi times this pi minus theta k. And skipping the details, the CL ideal is 2 delta F times sine theta k. So this gives us the incremental effect of flap on any airfoil, symmetric or cambered. So delta CL is 2 delta F times sine theta k. So this is how much the ideal CL changes when you deflect flap. And that actually is seen in real life too. So let's now think about what a trailing edge flap does. So summary of trailing edge flap effects is like this. Okay, let's take the CL versus alpha curve. Okay, so this is this solid line is the CL alpha curve for just the plain airfoil without the flap. So that's this. This is the plain airfoil. Some cambered airfoil, right? So alpha 0 lift is negative, but lift curve slope is pretty much close to 2 pi per radian, and there is CL max and stall. When you deflect a trailing edge flap, the alpha 0 lift becomes more negative. So it's flap like this. Okay, so this curve shifts to the left, or you can think of shifts up, doesn't matter, they're both the same. The slope remains the same, right? Thin airfoil theory says that slope is 2 pi per radian, doesn't matter what camber it is. And usually CL max increases, so there will be an increase in CL max. But when you deflect a flap, usually alpha stall decreases. So alpha stall will decrease. Okay, so usually this is what happens when you have a trailing edge flap. Now let's look at moment coefficient. So CMC over 4 is here. This is the baseline airfoil. It has a negative pitching moment coefficient because it's a cambered airfoil. When you deflect the flap, the CMC over 4 becomes more negative, because it's like increasing the camber in the rear part of the airfoil, right? So it kind of makes sense that it becomes more negative. So it will cause a pitching moment, nose down pitching moment. Now let's look at transition curves and the drag bucket. So if you have an NLF airfoil without the flap, maybe the drag bucket will be here. And so this is the CL ideal, right, for the basic airfoil without the flap. And that's because the upper surface transition curve goes like this. So this bend in the upper surface transition curve, that corresponds to the upper part of the drag bucket. So this drag bucket drag increases because laminar flow is lost on the upper surface. The lower corner of the drag bucket is when the lower surface loses laminar flow. So while the airfoil is in the drag bucket, both upper and lower surfaces have a good amount of laminar flow. When you deflect the flap, the CL ideal increases. So this, essentially this drag bucket moves up in the CL curve. So it moves to a higher CL. So this dashed line is the curve for with flap. And that's why in the previous page we said, and approximately it will be like this. The change, how much it moves up by is given by this. Again, this will work as long as you don't have flow separation here. Once you have flow separation, there's going to be so much pressure drag that all this goes out of the window, right? Skin friction drag will be so small, pressure drag will be so much that you can just forget about laminar flow. There's so much penalty due to pressure drag. So, but as long as there is no pressure drag, you can move the drag bucket up and down with a flap. And so transition curves will move like this. Upper surface transition curve will move up, lower surface transition curve will also move up. And this is actually used on some low-speed aircraft and sailplanes. Okay, so these are called cruise flaps. So these cruise flaps are usually small flaps, maybe 10% chord or 15% chord, sometimes maybe more, but usually 10-15%, because you want it to move by small angles and you want it to be small so that flow separation is minimized. But a cruise flap works by, so for example, let's say this is the basic airfoil drag bucket. Okay, so one of the things I hope you're seeing in the project too is that depending on so many factors, you will have only a certain CL width for the drag bucket, right? This is about it. So, but if your sailplane or aircraft, you want to fly here due to some thermal condition or something like that, some kind of, if you want to be in a climb, for example, or if you want to fly at slow speed for long endurance, or if you're a sailplane and you're inside a thermal gaining lift due to upward going air, you fly at slow speeds then. But then if you use the basic airfoil, you will lose all the drag benefit, right? You're flying outside the drag bucket. So that's when you can use a cruise flap and deflect it maybe 5 degrees down or 2 degrees down, something. Then you'll move the drag polar up, and then you're flying at the higher CL and you still have the drag bucket, you're inside the drag bucket. Likewise, if you want to fly at very high speeds, like you're going at maximum level flight speed, or you're like really going fast between thermals or something like that, you might fall below the drag bucket, and so you'll start consuming a lot of fuel or something. Then you put the flap a little bit up and you'll move the drag bucket down, and so you're actually moving the sweet spot to where you want to fly. And so that's where these are called cruise flaps, and They're used in many sailplanes and aircraft. Okay, so those were the two topics I wanted to discuss on completing the thin airfoil theory topics. So, okay, there's about 30 minutes, and I thought I'll first talk about this Newt 1 S0 Newton line. So how many of you are having problems with this? You guys were having, no, did you send an email? Oh, you figured it out?
I did have a lot of problems with it, so continue.
Okay. So maybe take 2 minutes to think about if you have questions on project 2. Meanwhile, I'll try to get MATLAB up and running. Yeah. Okay. So do you have some questions? Shall I proceed with this first and then go to the question? So remember that this Newt 1 S0 line is a way by which you can make a segment endpoint go to some desired x over c location. So here's the syntax. It looks really complicated, right? But once you distill it down, it's not too bad. So Newt 1 S0, that tells Profile, okay, I'm going to do this thing. IFTP1 has to be 400. Okay, so just don't worry about that, put 400 here. And JSEG IX1 is the segment number of the endpoint for which you want to set the X over C value. So let's say you're designing a 4-segment airfoil, and that's what I'm going to show the demo for. So let's say you have one segment here, another segment here, and this is 4. So 1, 2, 3, 4. And let's say this is at some 30% chord, and let's say this is at 32% chord, and I want to move this to 50. So this is a new location. And let's say I want to move this to 55. So this is the new location. So these two are desired X over C values for end of segment. EOS is end of segment 1 and 3, right? This is 1, 2, 3, and 4. We want to move 1 to 50% and 3 to 55%. So 1 is on the upper surface, 3 is on the lower surface. So you do it one by one. Okay, so we'll first take the first end of segment 1 and move it to 50%. So then this will become 1 because you want to move that segment. And to do that, you have to change the phi for this point, right? The phi is also, you have to use the end of segment 1 phi. And that will be, so this ITP will be 1. 1 means equal, this means I'm going to adjust phi. Like I think 4 means alpha star and something like that, right? So 1 in ITP 1 tells profile, oh, this guy wants to move phi. And then it doesn't know which phi. So let's think of the lower surface, okay? So I want to move, this is 400. I want to move the third segment. And if I want to move the third segment, I have to move the third segment's phi. So you've told profile you want to move phi, and then you have to say which phi do you want to move, and which phi is ITP2. So that is 3. Right? So this is end of segment, and this is end of segment. LLBOS just set to 0. I mean, this is like weird kind of code. What is LLBOS? It just means not beginning of segment. I want to do end of segment. Just put it as 0. It's just kind of too hard to explain. Just trust me, 0 is good. Okay, and this is where you want to move it to. You want to move it to 55%, so 0.55. And then clamp is optional. Like this is if your iterations don't converge, sometimes it's useful. And I don't know, for some reason, it seems like best to not use it for this particular line. Usually 1 works well. You can put 1 or you can put nothing. So that's how you do it. This is the lower surface. Okay, so I've got a profile file, and I'll put this on Moodle. This is a 4-segment airfoil. Let's go ahead and run it. Okay, let's run it so that we have only one. Well, it doesn't matter. So this is the airfoil, and it's plotting 2 velocity distributions at 2 conditions. I don't know what the conditions are. It's like 0 and 2 degrees. So the inner 2 velocity distributions are for 0, upper and lower surface, and the outer 2 are for 2 degrees. Just kind of looks a little weird because they all cross over. Maybe just to get some clarity, let's make it as 1. Let's just do 0 degrees. What happened? Did it run? Oh, yeah. You folks are better at this than I am. I haven't used it in a while. What's happening? It ran.
Yeah, I changed profile instead of
Oh, yeah, okay. All those things that I said, you have to pay attention to this, and I'm not doing it myself. Okay, let's open profile.in. I tell you, every time I go to profile, it takes me about half an hour to remember all these little things that I have to do. So if you feel like you're being tortured, you're not the only one. It's the same for me as well. So 1. But think about it. The people, people who used to do airfoil design in the 60s and 70s, like Wortman, Epler, they didn't even have these things. They had much lower utility tools, and they still did really great things. Okay, so here's some airfoil. Let's look at the upper surface, this point. This is segment endpoint 1. This is segment endpoint 3. Let's look at where it is. This is at like 0.32 or something. Okay, so this X over C is at about 32%, and this X over C is something like 45%. So now what we want to do is we want to move this to 50%, and we want to move this to 55%. And I'm just choosing some numbers that are different so that all those syntax things don't look all the same. So that's what I've done here. I've got 2 Newton lines. This is for the upper surface, and this is for the lower surface. So these are all comment lines, right? So if you uncomment the first one, you will set end of segment 1 to 50%, which is what is written here. Uncomment the second to set end of segment 3 to 55%. And if you uncomment both will happen. So since I just talked about the lower surface, let's just uncomment the bottom Newt line. And this is exactly what I think I've written on the paper. So on the sheet I wrote Newt 1 is 0, 400, 3. So 400 means this is the thing I want to do. 3 means I want to change end of segment 3 to some X value, and that X value is 0.55. And then that 0 is that weird LLBOS thing. Just put 0, don't worry about it. 1 means you're telling profile, I want to change phi, not some alpha star or something like that. So I want to change phi, and 3 in the end means I want to change the third phi. And then the last argument is clamp, which is optional, so I didn't even put it there. So let's save this and run it and see if it works. Okay, so it's happened. Okay, so you can see this is the lower surface phi, right? Lower surface segment endpoint 3. Earlier it was at 45%, now it's at 55%. It's exactly at 55%. I mean, maybe to some 5 decimal places or something, it's probably correct. That's why Newton iteration is so good. Now I can go and change all kinds of alpha stars and do all that other stuff. This will always be nailed at 55%. And so, it's a little bit of effort to figure out these syntax things, but once you do it, it's really cool. So just to show that, let me change the thickness. Instead of 12%, let's make it 16%. Right? Lots of things will change, but that will be at 55%. I hope. I haven't tried it out. So look at this. Thickness has changed, but this point is still exactly there. Okay, so I'll put this back to 12, and then we'll go and do the upper surface now. Okay, so now let's deal with the upper surface. I'll uncomment the upper surface Newt1 S0 line, and that reads Newt1 S0 400, and then 1. 1 means I want to move the x over c for segment endpoint 1, and that 0 is that LLBOS thing, and I want the x over c to be at 0.5, 50% chord, and then the next one is phi. The next one is I want to change the first phi, right? You're telling profile go and adjust the first phi to achieve this thing. So I'm uncommenting it out, and I'm leaving the second Newton iteration there, so both will be satisfied. And you go here, run this, and it's worked, right? So you can see this is exactly at 50%. Now let's go and change a bunch of things. Let's go and change 12% to 16%, and let's go and change pitching moment to minus 0.09, and let's go and change alpha stars to 7 or something. No, it's wearing. Let's go and change the lower surface alpha stars to minus 1. And I go and run it. Lots of things have changed. Look at this airfoil, it's so wildly different. But still, this is at 50%, this is at 55%. So that's kind of the power of this. Okay, so I hope this will help sort out the Newt1 S0 case. Okay, any questions on this part? Yes.
So you were saying that you need to watch out where if we have a bunch of segment endpoints that we're not trying to like jump over one of the other ones. We have like, so if you, let's say you want to move to 55, but there was one at 50, like that's kind of in the way, you'd either have to move that one too or like delete it or.
Correct. So you have to, you can't ask it to do impossible things because it's just a numerical method. It won't understand what you want. So let's say you had another segment endpoint here, right? So if that is at 40% or roughly there, let's say you haven't set a Newt1 S0 for that. So it's kind of moving around 40%. Then you go and make this fellow, this first one, go to 30%, it'll cross, right? And the Newton iteration will just convert, will just not know what's happening. It'll try to cross, and then profile, the map in the profile will crash, and then Newton it'll just kind of throw some weird error messages. And so you have to, maybe it's good to do a little by little and then move all of them in some way, or maybe you do the very first, like let's say you want to move everything towards the leading edge, right? You take the very first one near the leading edge and move that to some place. Put that Newton iteration first, then that will converge. Then you move the next one, because that's already moved, it's created some space. You can move the next one, then if you put them in order, they will just kind of like one will move, then the other one will move, and then everything will move. It might take a little bit of time to get that working if you have a bunch of segments. But I've done it. It's, once you think through that and do it, it's pretty useful. Okay, other project 2 questions? Yes.
Another one on that topic. It seemed like when you have a lot of segments that if you try to move it too far, it won't work. Does that seem right? Not just that it would run into another segment endpoint, but even if there's space, sometimes if it's more than a few degrees of movement, it seems like it won't.
I had a problem like that when I used a clamp. Did you put a clamp in this Newt line? Do you remember? How much was that value? Was it 1?
I think it was whatever was in your demo.
Okay. So one thing you can do, sometimes this will happen and you don't know why it's happening. It's just so airfoil dependent that I can't think of a general rule that always avoid this or always do this. those things work up to some point and then you get into your own particular case. So when that happens, you can replace this stuff. So profile.in is here, right? We actually used, so these are sort of the initial guess values for various things. And then the Newton iteration goes and changes all these things and comes up with something that you like. That means all of this is now changed. So if you go and look at profile.dmp, that's got all the changed values. Is there a way I can view left, right, or something? No, this way. Okay, something. So this is profile.dmp. Okay, and this is profile.in. So we started off with this, and then Newton iteration went and changed all this to this. So let's say I want to change the upper surface to 80%. I want to move that point to 80% of the chord. We have changed it to 50, right? So instead, if you change, let's say you try 80% and just not working, then something is happening and you're making the problem very difficult. So move it a little bit and take that converged solution. So you can actually take this converged solution, everything from foil all the way to ILE, right? Copy that and then overwrite this with that. Now it's got all the latest values here. This will immediately converge, right? Because it's already there and you're saying go there, so it's already there, it will converge. Now you can push it some more. From 50 you can make it go to 60, put that converge solution there, then from 60 you can go to 80, something like that. You go make it do little steps by hand, and then once it works, you might find in the process what is making it difficult. Maybe there's something there that you didn't think of, and so that's one way to do it. The other reason it may not work is maybe you're making it cross this point. It can't cross this x, this phi s. That is at, let's see, that's almost at 80%. So if you make this Newt1 S0 for the upper surface go to 80, let's make it go to 85. It won't work because you're crossing over that point and maybe you didn't realize that. It's probably bombed. Yeah, it said, something. The error messages take a while to understand what's going on. But if you look at this, that's why you're making it go past this. So instead you can make it go in smaller steps and say, well, maybe not 85, but if you go to 75, it'll probably work. So that's the 75%. So, maybe in future years I should think of giving a 4-segment airfoil as the template for project 2. Maybe that's a better starting point. So I gave something that's already very close, but then it's hard to change, especially if you're doing these things for the first time in Profile. Okay, chances are this will get you 75% laminar flow on the upper surface, but also there's a pretty good chance you'll have big laminar separation bubbles here, and that drag will go up. Okay, what else is giving trouble? So again, if this Newt1 S0 doesn't work, right? Another thing you can do is you can change all the phis by hand to get it close. Sometimes that might be just faster, especially if you were running into trouble with some syntax error with Newt1 S0. So move all the phis by hand, and that's just like subtract 2 here, subtract 2 here, subtract 2 here, something like that, Get it close, and then you can use Newton iteration to get it nailed. Okay, other questions on the course itself, general stuff?
Are you going to give out the final tomorrow and then it's gonna wait? I think that's what it's
Yeah.
for the syllabus. I should
Yeah, I
check.
think that's what I'm going to do. Yes. So let's maybe talk about that. There's still one more quiz. So there's a finals and there's a quiz, right? So quiz, I think this is quiz 7. Quiz 7, I needed to finish up this thin airfoil theory. So basically quiz 7, I think I'll put the stuff on the quiz, but I think it's basically on this one lecture. So oh, sorry, yeah. So quiz 7, I will activate it now. Is it okay if it's due on Sunday? I mean, it's end of the semester, you got to finish things anyway. Right? So that's quiz 7. Finals will be take home. Absolutely no collaboration, discussion, nothing, please. I'm trusting you on this. You can ask me any questions if you have any questions, but don't talk to each other at all. There will be 2 parts. The first part will be on Moodle. It'll be a timed test. I don't remember the time, but it'll say on the before you start the test, you'll know. And you can do this anytime before the submission due time. Okay, second part is paper questions. I think it's like 4 or 5 questions. So I'm going to give about 1 week. So I think I'm making it Friday, tomorrow's 12, December 1st. And then due probably, I think next Friday, right? Something like that. I don't remember approximately next Friday. As whatever it says in syllabus. Okay, so before I post the finals, I will shut off all access to the quizzes except quiz 7. So quiz 1 to quiz 6 will be made invisible. So if you want to download them, you should do that before the finals. I'll send out an email with the time when I will actually turn these off. Quiz 7 is overlapping with the finals, so I'm not going to touch it. I'll just let that be there. Any questions? So that's the plan. So just because I'm giving 5 days doesn't mean it's going to be a long test or something. It's just that I'm giving flexibility, especially with a lot of the distance ed students. They have other work commitments and so on, right? Okay, some of these will be a little bit open-ended, so it's not going to be a completely clearly defined problem or problem with one answer. It might involve some airfoil design, something like that. Okay. Nothing else? Okay, thanks. I hope you had a good semester and found this course interesting. Yeah, before I forget, please do the course evaluation. We do take these things seriously and make changes to the course based on feedback, so please do that. Okay, thank you.